Thank you so much for staying to the ultimate talk of the day. I appreciate it very, very much. So today I'm going to be talking about some tests that we did in ending up last January, multi-degree of freedom hybrid simulation with bearings, focusing on bridge bearings on top of taller piers. And so going back not to bridges but to buildings, sort of my interest in this topic started when we were thinking about reduced cost retrofits for using isolation for reduced cost retrofits. And so when you do a retrofit with isolation, it's often very, very expensive. A lot of work at the foundation level, need for an extra diaphragm layer to construct, and this can be cost prohibitive. And so we were thinking about, well, what if we instead put the isolators at the top of the columns? What's sort of the limit of the stiffness that you need in the supporting columns compared to the isolators? Because what can happen is you can start having rotations at the tops of those columns because you're releasing that boundary condition, and that rotation at the top of the column goes into the isolator. And we typically design isolators to have parallel top and bottom behavior. So we did some analytical studies on friction pendulum bearings a long time ago, looking at how their stiffnesses changed, the displacement capacities changed. And then we started doing some tests on rubber bearings on tops of columns. So these were done about 8 years ago. And these are just quasi-static tests where you have a column, then that's a natural rubber bearing, and then on top we were actually applying a rotation as well. And we did a series of these small-scale tests, about a quarter scale, where we are now allowing that rotation in the bearing. And we looked at all different column sizes, where the one on the left is sort of comically small and you would never allow, but just sort of adds to our data set so we understand trends in design. And so this is the same setup, a different set of tests where we actually just turned it upside down. But you'll see this is with that very slender column. As we go further and further out, you're going to see more and more rotation at the boundary condition between the rubber bearing and the column. So you will start to see that rotation that we ignore in design. And we typically ignore in design because just if you look in the building next door with these isolators, you have very large rigid diaphragms on the top and bottom. So it's a very sound boundary condition to assume. But this is just for novel applications. So those very large rotations you saw at the when we have larger displacements, you can see it starts really wiggling out. And so from this data, we looked at trends and changes of the horizontal stiffness. So what you see here is for two different pressures, axial loads on the bearings, and when 100% would be no change in stiffness horizontally. And you can see as you start having larger and larger rotations, you have this trend downwards in the shear stiffness. So there's definitely a relationship between the rotation and shear in these bearings. And so we started thinking about how this might affect other systems as well. So bridges do not have diaphragms below their isolator layers. So bridges, if you have sort of a general overpass and it's isolated, it's a nice stocky support in the pier, you're not going to have any rotation. It's a non-issue. If you start having much larger piers, then you will start having some more flexibility and maybe some rotation at that boundary condition. So this is a bridge, the Coronado Bridge in San Diego, and this bridge is not necessarily an isolated bridge, but it has many piers that are isolated. The idea is really to decouple the behavior of the piers from the deck and the bridge. And so you can see these are very tall piers, and then you have isolators seated above them, and this is in a highly seismic zone. So why not just use numerical models to understand this behavior? So there is a major lack of data for the horizontal-vertical interaction of these bearings. So you saw the tests that we did. We have those tests, those cyclic tests. There's a couple other groups, that, particularly in Japan, where they sheared the bearing and then applied a series of rotations and then repeated that at multiple axial loads or shears. There's just very few data sets for this, and there's none with actual seismic input. Then there's a lack of implemented models. So there are these whole series of mechanical models that are very beautiful, but hard to calibrate, and only one is actually implemented in OpenSeas, and it's highly unstable to use. And then on the other hand, you can just simplify the rotational behavior as a linear spring, and that's another viable way. So those are our two options right now if we want to consider this just numerically rather than experimentally. So we set off to do an experimental hybrid test in the lab at UC Berkeley on the second floor. And so you can see the Coronado Bridge, yes, indeed, is 3D, but we made it 2D for our playtime. And so we have a 2D model of that bridge, and you can see that piers 2 through 14 are isolated. And so you can see we have one physical element, just like Gilberto mentioned. Wouldn't it be nice to have 12 bearings, all with different demands? Wouldn't that be lovely? But that's not really possible, right? But as you can see, all of the pier heights are changing significantly. So the demands on the bearing on top of pier 2 are going to be drastically different than the demands on the top of pier 14. And that's where we started thinking we should be using model updating. Unlike for the case which we did for the steel testing that Professor Mosqueda just talked about, where we did looked at the substructuring elements, not the main element, not the column. Here we're looking at the main element of our physical test. So we were physically testing what we called bearing on top of pier 14. We used that information to update our knowledge on all of the other remaining bearings and proceeded with the numerical side. So if you look at our setup, very common, we were using OpenFresco as our interface between our experimental and numerical. And we were doing our model updating in Python. So the only updates we needed to do to OpenFresco was to introduce that feedback, the ability to talk with our model updating algorithm. And then in OpenSeas, we had to modify some of the elements that we were using so that we would be able to update their parameters throughout the testing. This is our experimental setup. As you can see, it's testing in plane. And so we aimed to control 3 degrees of freedom: horizontal, vertical, and rotational. So we were using, instead of trying to control at the actuator points, we used the MTS's DOF control right above the isolator. And because we didn't have such complicated nonlinear issues like Professor Mosqueda discussed vertically, we were just using a simple spring stiffness to convert to displacement commands for our vertical. So for our experimental test, we used a 1/4 scale bearing, or sorry, 1/3 scale bearing. So it's actually quite large still. The real bridge had 4 sets of these at the top of each pier. So we made sure that when we interfaced between the two, we had to use our scaling laws as well as number of bearings. And then for our numerical model of the bridge, everything, our piers had nonlinear beam column elements so that we could get yielding in those elements if we needed. And we had very simple supports for our abutment and our piers. So this is very important. When you are doing model updating, you are confined to what you are updating. So it is very important to choose wisely at the outset. And so it's a combination of what you think you can do and what you can update experimentally versus what you think you're going to need to capture in your experiment. So for example, for the steel building, we would have loved to have used and model updated an IMK model, but it was too tricky because of the piecewise linear behavior and the number of parameters. So for the updated version, we used just the book win instead. And so that was that, trade-off between what we would have liked to do versus what we thought could do with our algorithms. So here we used axial degree of freedom for vertical, and we actually kept that constant. We did not update that. And then we had a book win for our shear and a rotational, or bilinear for our rotational degrees of freedom. And you can see that we minimized the number of parameters we had to update during our testing to what we thought would help us tune in to the correct behavior. And so again, here are our the models that we were using, and importantly for the shear and bilinear, we added these interaction terms so that you could see the interaction between the shear, the rotational behavior, and not just conflate that with the original model terms. So for our parameter identification, we used the unscented Kalman filter with a few modifications that other groups have done as well. Number one is we applied constraints, so that makes sure that the values that you're predicting, that you're identifying from your data, do not exceed those that are not physically available. We also provided weighting. And so this measurement weighting we used to actually understand when we needed to be learning. So you can imagine that we understand the performance pretty well under small shears, small rotations. It's pretty well understood. It's those large excursions where we're really learning new information. And so this weighting parameter says, okay, I'm going to really ramp up my learning when I have very large displacements. And then what else happens is with this algorithm, you're learning at every single time step. So say you have a very large excursion, and then you have many, many small excursions. You don't want to have, forget your memory of what you've learned previously. So this weighting parameter helps say, okay, when I have these really small excursions, I'm not going to learn as much. I'm going to keep the behavior that I've learned previously. And then this last term is this adaptive calculations. And so we have two parameters here, Q and R, and those are for our process noise and our measurement noise. And this is really helping you determine if information is noise or new behavior that you haven't seen before. And it's quite tricky to really tune these. And so the adaptive portion of this helps it so that you are not quite so stuck with your initial parameters. But even so, your initial choices for these Q and R actually tend to be very important to your findings. So, for example, I'll talk later about this R value. We set this based on what we predicted our maximum force would be for all of our ground motions. And it really does change how your model updating works. So we used, well, I'm going to show two ground motions that we used. Here, they were scaled by some good friends who were seismologists for our local site. And so we use ground motion 1 is from Cape Mendocino, and ground motion 2 is from Uwate. And then we scaled these 1, 1.5, 2. And I'm showing this not to skip to the results, but to talk about why I'm showing these two ground motions. So what you can see is ground motion 1 has much, much larger rotational. So here I have the shear demands, the rotational demands, and then the shear hysteresis the rotational hysteresis. So you can see that in the end, ground motion 1 has much larger shear and rotation demands, which is going to affect the performance. So we wanted to see how the model updating worked for both situations. And then if you look at the time series, ground motion 1 has very large displacements up front, whereas ground motion 2 has moderate displacements sort of throughout. And those two things affect your learning rates. So here is the testing setup, or testing. This is from ground motion 1, scale factor 2. We were not testing anywhere near real time due to limits on our hydraulics. We tested initially at 5 times slower, 10 times slower, and 17 times slower of real time. And we saw no significant difference in the bearing hysteresis, but did find difference in our tracking, so we went with the slowest moving forward. We were not inhibited at any of those time steps with the addition of our model updating algorithm. That did not slow us down further. So, if we start looking at the ability of our model updating, so the blue, so we have our shear hysteresis and our rotational hysteresis. And I'm showing ground motion 2 first because that was the ground motion with less displacement, less rotational demands. And so the blue was our initial best guess data. So we didn't try to choose bad parameters to adjust from. We chose our best guess parameters using analytical solutions for the stiffness and strength of these bearings. So the blue is our initial guess for what these bearings should be doing, both in the shear and rotation. Red is our instantaneous prediction. So at every single time step, we're getting back data, we're selecting new parameters, and this is what the force is from that. And then you'd like to, at the end of these tests, have a steady set of parameters that you can use for future numerical models, right? And so that's what we have for our final data, the green that we're showing. So you hope that at the end of your test, you don't have model parameters that are particular to that last time step and are unusable. You want something that is robust and usable further. So you can see that we were quite happy with these responses. So blue is quite far away. Red starts off, not so nice, and then converges to where you're seeing the experimental. And the green, we're happy that we've stayed at a very nice fit at the end. Okay, ground motion 1 had larger displacements and shears. And here you can see that for our shear results, we were quite happy. Rotation, what happened? Well, you have this softening in the rotational degrees of freedom under large rotations, and then coupling that with the shear. And we did not have a model that was capable of doing that. So it's very important when you're selecting these models up front to choose something that you think is really going to be able to capture any behavior that might be salient to your structural response. So it's a very critical step. So this is a boring slide, but so what you can see is we have on top, I'm comparing the damping that we predicted to the damping from the physical experiment. And you can see going from your initial predictions here to your final predictions at the end, we have much closer energy dissipation. And then down here, we have the root mean squared error in our force predictions from our initial, and then the reductions. So you can see we have about an 80% reduction in the shear force predictions when we do our model updating. Okay, and so the other thing we looked at is the parameter convergence. So Gilberto showed some of these. We're tracking how our parameters are changing with time. So for ground motion 1, we had fairly good convergence at the end of our testing. And that was the ground motion that had the largest upfront motions and the largest displacement. So you had these big upfront motions, caused great changes in your parameters, and then the motion sort of died down, and so it was more stable. Ground motion 2 had sort of more continuous long motions throughout. And you can see it didn't really converge in all instances towards the end. And so the problem here is that we set that value for the noise, that R value I talked about previously. We set it based on the largest forces we thought we'd see in the test, and that was for ground motion 1, not ground motion 2. So because our measurement noise was set based on that, we weren't really, we weren't choosing that things were new information. We were treating them as noise. So when we reduced that R, we were able to get much faster parameter convergence. So my students spend a lot of time on model updating. And I think it's really important to reflect on that and say, I didn't just use a shiny tool for the sake of using a shiny tool, and did it actually make a difference in my experiment? In the results. And so here you can see this is for ground motion 2, scale factor 2, and this is for every single, the bearing, or every pier and every bearing at every pier. And what is the difference between if you just used your best guess parameters in your hybrid simulation versus this model updating? And you can see in these piers that are short, where there's not a lot of rotation, there's not a lot of difference, right? But when you start getting to these taller piers where you are taller and you don't understand that rotation shear behavior as well, you do start seeing about a 20% difference in the behavior there. So I think it was worth it. We also took this chance to just explore what effects things would have on model updating. So one is how having bad parameters initially would affect your response. So we know it's isolation, we have some pretty good guesses, but what if you went in and you didn't have a lot of idea of what was happening? So what if you had poor parameters? So we changed to what we called a rough guess. And so you can see the initial prediction was way off because this is our rough guess, we're just playing. And it takes a little bit longer to converge, but at the end you're getting to the same models. So we were pretty happy with how robust we were into converging to the correct model. And so you can see that here. The other thing that we wanted to think about, and we were able to do this because we had a system that was not going to be damaged, is how important is that initial selection of what your physical element is. Because you can imagine that if this was instead the steel test, you only get one shot there. You have to choose the best element that's going to represent your structure. And so what we did is two scenarios. The first scenario is what we did all along. We tested what we called the bearings on Pier 14. We did model updating, all that fun stuff, but we collected the displacement time series from the bearings on top of column 7, and then we ran that through the bearing as if that was just a controlled displacement time series, and then compared that physical data from the controlled displacement with what we had predicted for the bearing with the model updating. So how well is that model updating actually getting what you have? And then we switched it. Then we said, okay, the bearing at top of Pier 7 is now our physical element. How well is that predicting Pier 14? And so this is not, these are all experimental results. None of these are our model updating or numerical. I just want to point out, it's important to note that the bearing at Pier 7 was stiffer because it had less rotational behavior. So less rotational demand, less coupling, so it had stiffer behavior. So it never saw the softening from the coupling. And that affects how the model updating happened. So if we go to our, what happens with the model updating, for scenario 1 on the top, I have shear and rotation. It actually, so it starts off rocky. So the red is the model updating. It starts off poor. But then when we're trying to predict bearing 7, you can see the final model in blue. The peak forces are actually quite similar to the black. So you're having a good prediction, we would think, of the bearing on top of figure 7. Down below in scenario 2, when we're using the bearing on the shorter pier to predict the taller pier, you can see that even at the end, when you compare the blue to our experimental results, we're overshooting the force because we're never reducing the stiffness based on the rotational behavior. So you're not being able to actually learn that full interaction. So did this make a difference? It made a difference about 8% in the bearings that did have more rotation. And generally, our root mean squared error, when you looked at the local model level, was about 42% less for scenario 1. So our model updating results, we're happy with how we implemented it, and it lets us understand more complex system level behavior where not every physical element can really be tested. But it's very dependent on which physical element that you're selecting. So we think you should always be selecting what you think is going to have the extreme behavior. And we need to work further on performance of parameter identification because it's really dependent on the filter variables you're using, the method you're using to find that parameter identification. And the ability to capture that behavior is totally dependent on what model you use. So you saw the bilinear model was not getting that softening behavior. So it requires really careful consideration. And we're also looking at if you can do some sort of adaptive combination of models that are selected throughout the test. I want to move on really quickly through the full system. Did the model updating, was it a helpful tool for us to understand the system level behavior? So on the left, I have a numerical, these are both numerical models, but this one is with the bearing, shear, and rotation behavior that we truly learned, our final parameters from our experimental testing, versus what if we just ignored any rotation? So what if we have rigid boundary conditions? So if you do that, you can see that the numerical model, if you ignore any rotation, is going to severely underestimate your pier drifts and your shear strains. And this continues even larger at scale 2 when you get to bigger ground motions. And so we incorporated this into sort of a fragility calculation where we looked at a larger number of ground motions and looked at damage states. And we chose these damage states that are often used by Caltrans, where getting larger is a worse damage state. So we looked at damage state 3, moderate, and major, damage state 5, and used some numbers provided by previous researchers for drift limits for piers. And we came up with our own sort of damage states for bearings, where we said damage state 3 was based on this this overlap method for post-buckling limits, which is known to be to underpredict the buckling limit. And then we said full overlap was damage state 5. And using that, we could compare what happens if you are including this rotational coupled behavior versus having vertical or parallel boundary conditions. And you can see there's a significant decrease in your capacity of your bridge if you include that full coupling. But this makes my research look really great. So let's look at some other simplifications you could use, as you could just model the rotation as a spring, including no coupling, and what difference would those two make then? It's much smaller. So it's about a 5% decrease on the median of those fragility curves, so it's not actually significant. So it is important to include the rotation. It is not, super critical for at least this structure to include those full interactions. But it sure was fun. So thank you very much.